and welcome to STEM Pursuits with Mr. Clausen. Today we are going to give an introduction to complex numbers. So a couple of things that we're going to look at today. We're going to talk about how to simplify complex numbers. We'll introduce what complex numbers are. We'll look at some writing format stuff with complex numbers, and then we'll look a little bit at some of the calculations that you can do with complex numbers, including absolute values and finding additive inverses. So let's get started with today's lessons looking at these key skills. So one of the things that I want to talk about in terms of simplifying complex numbers is just simply introduce what a complex number is. A complex number is really just a number that is not real. Now you might be thinking, why on earth are we doing this? Well, the reason that we're doing this is because in certain areas of mathematics, especially abstract mathematics, specifically in applications where we can apply to computer science, there are situations where we can get non-real numbers. We can get negative square root values. And whenever we encounter these values, we refer to these as imaginary numbers, because the thing is you can't multiply two numbers that are the same together and get a negative number. You multiply two positive numbers, you will always get a positive number. And if you multiply two negative numbers together, you will always get a positive number. So the idea of a negative square root is not real, but they do need to be accounted for, because sometimes when you're looking at higher ordered polynomials, so things like quadratics, like we're talking about in this specific lesson, there are sometimes solutions hidden in the form of a complex number. So one of the very first things that we need to talk about here is looking at, well, how do we just even write and work around these abstract ideas? How do we take an imaginary number and rewrite it as a simplified complex number? So what we need to do is, at this point, just look at things like the square root of negative 7 and then separate this out into the square root of negative 1 times the square root of 7. And what this allows us to do is it allows us to kind of pull out the real part from the imaginary part, and then this imaginary part we can substitute in a variable, because as I showed over here, the square root of negative 1 is equal to I. And all we need to do in terms of simplifying a complex number is to pull this out and just simply rewrite it as I times the square root of 7. And right now, this is all we're looking to do. Is just simplify these out, get these new solutions out, and look at this. So the other thing that we can do is, if we're looking at a little bit larger example, I want to be able to do the same thing. So I want to be able to pull out square root of negative 1. I want to be able to multiply that by the square root of 32. Okay, again, kind of pulling out the real part from the imaginary part. Okay, so this will be equal to I. And then the square root of 32 can be simplified a little bit. So the square root of 32 would be equal to the square root of 2 times the square root of 16. And if you see that, that's a perfect square. So the square root of 16 would be equal to 4. And what this allows us to do is it allows us to write out this new simplified complex number. So with this, we have a 4, a square root of 2, and an I that are left over here. So 4i times the square root of 2. So whenever you're writing this out, part of the reason I include this example is this is typically how you should simplify a complex number. Okay, the multiplier by the imaginary number times the square root of 2, the irrational part that's left over. So that should give you a simple idea of just how to interact with these at a basic level. Writing format for complex numbers. So whenever you do have a actual imaginary component, and you have a individual real component, there is a specific A plus BI format that is encouraged for you to use. And this will make a little bit more sense as we get onto day 2. But whenever it asks you to write complex numbers in the correct format, this is what it's looking for. So when we're looking at 8 and the square root of negative 8, what we want to be able to do with that is we want to say 8 plus whatever negative square root of 8 comes out to. So we do need to look at this. We do need to split this out. So for example, negative 1 times negative 8. Negative 8 can be simplified because that's equal to the square root of 2 times the square root of 4. Square root of 4 is a perfect square that equals 2. So this would equal 2 square root of 2. But there is this I component here. So when we go and we write this out, this would equal 8 plus 2i times the square root of 2. And that would be your solution in the a plus bi format that we have listed here. And again, the same thing would apply here. We can split out negative 1 times the square root of 4. And this would be square root of negative 1. So this is equal to I. And as you may have guessed, the square root of 4 is equal to 2. So when we write this out in the correct complex number format, this will equal 3 plus 2i. And then that would be your simplified expression. Okay, so again, just looking at some basic formatting stuff. How do we write this out? How do I want you to write this out to simplify our process as we move on? Now, finding absolute values of complex numbers. And this might seem like the most arbitrary idea, but I think one of the things that I want you to do when we're keeping in mind with this is whenever we're looking at a complex number, we have to think about it in terms of that you have a number and you have it in you always have two components. You have a real component, just like when we were writing it out before, and we have a imaginary component. And in computer science, when you get these numbers, sometimes they still have a value associated with them, even though that they're not real, like they're trapped like in that specific circumstance. So we still need to know what value that they have in terms of their magnitude. And what I mean by that is that whenever we're looking at imaginary I and real X as like an example here, we want to be able to look at a value like the absolute value of negative 7i and know what its actual magnitude is. So when we're looking at a situation like this, if this is the origin of the real imaginary plane, what we want to be able to do is go, all right, how far is it from the origin? 1, 2, 3, 4, 5, 6, 7. In negative 0, so 0 real component, and negative 7 imaginary component, this should have a magnitude, a distance of 7 from the origin. So literally what is happening when we find an absolute value is we're really making a derivation from the Pythagorean theorem, more specifically the distance formula. So if you go and you square the real component, which is just 0, and then you add the imaginary component and square that, this will simply equal the square root of 7 squared, which would be equal to 7. And you can find the absolute value of complex numbers using this method. Now let's look at an example where there's an a plus bi format here. So you have the real component plus the imaginary component here, just like we practiced in the writing format. So in this specific situation, we can go look at our axes. We can go 1, and then we can go 1, 2, 3, 4. So this is at a real component of positive 1 and a non-real component of negative 4. And what we can do is we can look at the distance from the origin to that point. And we can tell it should be a little bit longer than 4 or bigger than the square root of 16. And so what we're going to do here is we're actually going to test this out. So we're going to go and multiply or square, more specifically, the real component. And then we're also going to square the imaginary component, and this will get us 1 plus 16. And this will get us an absolute value for 1 minus 4i of the square root of 17. So whenever you approach these problems and you see these, I would write these down on a note card as far as the format, all right? So maybe even include an example, because this is something that I find students forget. It isn't something that we spend a lot of time on, but it's something that I do want you to know and be able to calculate in terms of absolute values of complex numbers. So, last thing that I want to look at, finding additive inverses of complex numbers. And I'm hoping one of the things that you're getting from this idea of complex numbers is that a lot of the mathematical operations that we're dealing with here with complex numbers are the same as that for real numbers. So when we talked about additive inverses at the very first lesson of the year, lesson 1.1, one of the things that you guys saw is that an additive inverse of something is simply its opposite. And if you want to find the opposite of something, you just take a number and you multiply it by -1 or a minus sign. So the additive inverse of 4i is simply -4i. And it works the exact same way. And really the only thing that you need to think about the I variable is like a variable. Think of it as like an x, just with a very specific value. And the same thing would occur with 9 plus I, and you'll multiply it by -1. And what you'll get as a result, make sure you distribute that minus sign to both terms, you'll get -9 minus I as your solution. So I hope you found this video helpful and that you have a great rest of your day.